And welcome back to another lesson, MCV4U. Today we'll be talking about concavity and points of inflection. So let's look at what defines something as concave up or concave down. So here we see that the graph of a function has concavity upwards if the graph lies above all its tangents, if the tangents rotate counterclockwise, if the slope of the tangent lines increase, and if f prime of x increases or f double prime of x is greater than 0. So here we see that on the right, it shows a picture. The slope starts at -2, and then there's a slope that's equal to 0, and then the slope becomes 3. Here again, we see that at the slope of 0, we'll look at something called points of inflection, which we'll look at in this lesson as well. And then here, the graph of a function has concavity downwards if the graph lies below all its tangents. The tangents now rotate clockwise instead of counterclockwise. The slope of the tangent lines decrease, and then f prime of x decreases, or f double prime is less than 0. And so here we see that the slope starts at 3 and gets to the slope of 0, and then the slope of -2. Okay, so when we look at the test for concavity, so again, suppose that f of x is twice differentiable. So here we know that that's f double prime of x on the interval as x is from point A to point B. So if f double prime of x is greater than 0 for all x values from A to B, then f of x is concave up over that interval. If f double prime of x is less than 0 for all x values from point A to point B, then f of x is concave down over that interval. So it's just, okay, so here we're really looking at the second derivative here and what that will tell us, again, if it's concave up or concave down. And then finally, if f double prime of x is equal to 0, then the function has no concavity at x. And so this is important as we go through these examples. So here, let's look at example number 1. So example number 1 says, for each of the following functions, determine whether each is concave up or down by examining the first and second derivative and sketch the functions. So here we see that we have y is equal to x squared. So first derivative is y prime is equal to 2x. And here you see that y prime is equal to 0 when x is equal to 0. And here we see that our first derivative is never undefined. And here we're not looking at a rational, and so we do not have any undefined points. And so here, if we draw our number line, so here we have negative infinity, 0, and positive infinity. Okay, so here if we sub in a point such as -1 from negative infinity to 0, see that that's going to be negative. And we know that when it's negative, that means it is decreasing. And here, if we sub in a value like 1, 2 times 1 here will give us a positive value, and we know that that is increasing. So here, if we look at our second derivative, so if we derive now 2x, we'll be left with 2. So here we see that our second derivative is always positive. Again, what that means is that f of x always is concave. Okay, so here, if we graph our function, so here we see that we have a parabola here. And if we graph the parabola, it will look like this. And so how can we describe this parabola here? And so here, initially it's decreasing, and then once it hits zero, then it is increasing. But here we see that throughout the entire graph, it is concave. Okay, let's look at a more difficult example here. So it says determine the intervals for which the following function is concave up. So here we'll find the first derivative. So y prime is equal to 12x cubed minus 6x squared minus 24x. Here we find our second derivative, so we'll derive that again. We'll get 36x squared minus 12x minus 24. Here, what we're going to do is we're going to take out a common factor of 12, and we'll be left with 3x squared minus x minus 2. So here we need, again, two numbers using decomposition, two numbers that multiply to equal to -6, and the same two numbers need to add up to equal to -1. Those two numbers will be -3 and 2, and -3 and 2. So here, we factor that out. We have 12, 3x squared, and we'll replace the negative x with the two factors. So it'll be -3x plus 2x minus 2. And the 12 still stays on the outside. And so here, if we factor again by decomposition, we get 12. Here we'll factor out a common factor from the first two terms, which is 3x. We're left with x minus 1. And we'll factor out a 2 from the last two terms, which will be left with x minus 1. And so here we'll have 12 x minus 1, 3x plus 2. So here, what we can see is that y double prime, or the second derivative, is equal to 0 when x is equal to either 1 or x is equal to -2/3. And here, we see that y double prime is never undefined. Okay, so here, then we can again draw a number line or a chart, whichever one you prefer. Here we'll draw a number line. So again, we have our positive infinity, negative infinity to positive infinity, and we have our different points. So we have -2/3, and we have 1, positive 1. So here, if we sub a value that's less than -2/3, so we'll sub in -1 into this equation. So here we see that 12 will be positive, -1 minus 1 will give us negative value, and then 3 times -1 plus 2, that will give us a negative value here. So here we see that it's going to be positive in terms of the second derivative, which means that it is going to be concave. Or we'll use the short of CU. Here from -2/3 to 1, and our 12 is still positive. So we'll sub in a value of 0, for example, 12 is still positive. 0 minus 1 will give us a negative value. And 3 times 0 plus 2 will give us a positive value. So positive times positive will give us a negative value. So give us a negative value. So that means here in the second derivative, it will be concave or, or CD. And finally, from 1 to positive infinity, let's sub in a value of 2, for example. Here, 12 is still positive. 2 minus 1, that'll be positive as well. And then 3 times 2 plus 2 will be positive. So here, see that's also positive. So that is also concave up or C. So here we see that, therefore, function is concave up for x. So from negative infinity to -2/3, and also from 1 to infinity. And so here, as we've been looking, so the first derivative will help us determine the intervals of increase and decrease. And then the second derivative will help us determine the concavity. So again, concave up or down. So here, when we look at points of inflection, a point on a graph is called a point of inflection if the concavity, so if the concavity of the graph changes at that point. Inflection points may occur at points where y double prime is 0 or y is undefined, or y double prime is undefined. So here it says use example 2 to identify the points of inflection for y is equal to 3x to the power 4 minus 2x to the power 3 minus 12x squared. So here we notice that the concavity changed at 2 points. So it changes at x is equal to 1 and x is equal to -2/3. So here if we sub in x is equal to 1 into our equation, so y is equal to 3 times 1 to the power 4 minus 2 times 1 to the power 3 minus 12 times 1 squared. Here we'll get an answer of 3 minus 2 minus 12, which is equal to -11. And so our first point here will be at 1 and -11. And here if we sub in x is equal to -2/3 into the equation, y is equal to 3 -2/3 to the power 4 minus 2 -2/3 to the power of 3 minus 12 -2/3 squared. And so here we have y is equal to 3. And here it's really just 2/3 to 2/3 to the power 4. And so because it's a even exponent, again, the negative will become positive. So here 2 to the power 4 is 16. 3 to the power of 4 is 81. Here we have -2. And because it's odd exponent here, the negative will stay. So 2 to the power 3 is 8. 3 to the power 3 is 27. So -8/27. And here another positive exponent, so it's squared. So 2 squared is 4. 3 squared is 9. And here we can simplify. So the 3 and 81 can simplify, and the 12 and 9 can simplify to 4 and 3. So here, if we write this, we can rewrite this as 16 over 27 plus 16 over 27 minus 16 over 3 once we expand it out. So here we have 32 over 27. And if we make 16 over 3 with the common denominator of 27, multiply both 16 and 3 by 9, we'll get 144 over 27. So 32 over 27 minus 144 over 27 will be equal to negative 112 over 27. And so our second point here is equal here to negative 2 over 3 and negative 112 over 27. Okay, so here we write our therefore statement. So again, therefore, there are points of inflection at 1 and negative 11 and negative 2 over 3 and negative 112 over 27. Okay, so let's finally find this last value. So, or this last example. So here it says find the intervals of concavity and the x values of the inflection points for f of x is equal to x squared over x squared plus 1. So here, let's derive this function. So f prime of x, so here we're going to use quotient rule. So derive the top, keep the bottom subtracted by the top, so keep the top, and derive the bottom, which is 2x, and then the bottom squared, so x squared plus 1 squared. Here, if we expand this out, we get 2x to the power of 3 plus 2x minus 2x to the power of 3 over x squared plus 1 squared. So here, to 2x to the power of 3 will cancel out. And so here we'll be left with 2x over x squared plus 1 squared. And now we're going to find the second derivative of this function. And so again, we're going to use quotient rule again. So here we'll derive the top, which is 2, and we'll leave the bottom x squared plus 1 squared. And keep the top, and we'll derive the bottom, so outside first, and the inside. And then that's all over x squared plus 1 squared, and then we're going to square that again, so it would be to the power of 4. And here, now we're going to simplify this a little bit. So we have x squared plus 2 times x squared plus 1 squared minus 2x, and then we'll simplify things inside. So here, if we simplify values inside, sorry, so if we simplify this inside, we'll get x squared plus 1 minus 4x squared. And here, it's over x squared plus 1 to the power of 4. So here, if we rewrite this, we have 2x squared plus 1 and negative 3x squared plus 1 over x squared plus 1 to the power of 4. And so here, if we look at a couple of solutions, so look at x squared plus 1 is equal to 0, x squared is equal to negative 1, and we can't square root a negative, so here there'd be no solution. Then we'll look also at negative 3x squared plus 1. So negative 3x squared plus 1 is equal to 0. 1 is equal to 3x squared. 1 over 3 is equal to x squared. And so here, x will be equal to plus or minus square root 1 over 3. So here we see that the second derivative, or f double prime of x, is equal to 0 when x is equal to plus or minus square root 1 over 3. Or again, approximately here, plus or minus 0.58. And so that'll help us when we're finding values here. And here we see that f double prime of x is never undefined. So here, if we draw our number line, or if you prefer the table, so here from negative infinity to positive infinity, and we have a couple of points. So we have negative 1, so we have negative 1 over square root 3. We have positive 1 over square root 3. Okay, so negative 1 over square root 3, positive 1 over square root 3. Sub in a point, again here, that's less than negative 1 over square root 3, so here we'll sub in negative 1, sub in negative 1. We have positive value for 2, sub in negative 1, so negative 1 squared plus 1 still be positive, negative 3 times negative 1 squared, so that'll be negative 3 plus 1, that'll give us negative value. And then at the bottom, sub in negative 1, so negative 1 squared plus 1 to the power 4 will give us a positive value. And so here we see from negative infinity to negative 1 over square root 3, that will be negative, which means that it is concave down. From negative 1 over square root 3 to positive square root 3, we'll sub in 0. So here, 2 is still positive, 0 squared plus 1, positive, negative 3, 0 squared plus 1, positive, and then 0 squared plus 1 to the power 4, also positive. So here it would be positive and concave up. And finally, from positive 1 over square root 3 to infinity, so sub in a value of 1, for example, if we sub in a value of 1, again, 2 is still positive, 1 squared plus 1 is positive, negative 3, 1 squared plus 1, that will give us a negative value, and then all over 1 squared plus 1 to the power 4, which is positive. So here, we said to see that this will be negative, or concave down. So here, if we look at the intervals of concavity, so again, f of x is concave down when x is between negative infinity and negative 1 over square root 3, and also between 1 over square root 3 and infinity. And then f of x is concave up when x is between negative 1 over square root 3 and 1 over square root 3. That means that there is a point of inflection points of inflection at x is equal to negative 1 over square root 3 and x is equal to positive 1 over square root 3.